So in the last video, we did the sort of initial kind of graphical, the sort of thinking through graphical abstraction and thinking about what the coordinate system is for this Caber-Toss problem. I will note in the coordinate system that actually we probably would choose a slightly different coordinate system by the time we got to step 4, fall. It would make sense in this case to stop thinking about x and y as being coordinates at all. If you're actually saying it's pinned here, you would simply use theta. But the next step we'd like to do is actually go from this sort of coordinate systems and having decided what the interactions are to actually building mathematical models for the interactions and also expressions, what the angular momentum and so on are. So let's actually first, we're going to focus on this first step of, actually no, let me change that. Let's focus first on the step of flight. That's the simplest of the 4 parts of the motion. And I'm actually going to do the sort of flight case in 2 ways. One of the ways is really kind of dumb but emphasizes the point, and the other is a whole lot simpler. So let's deal with flight, and we'll do flight first in the not so bright way. And when I say the not so bright way, what I actually mean is that our choice of coordinates for this and the way that we write the equations is not going to be as compact and simple as it could be. So we're going to think about the position of the center of mass, and we're going to think about what the angle of this thing is, and we're simply going to use this as our origin for everything. Okay? So if we use that as our origin for everything, our task is to figure out how do we write the momentum, how do we write the angular momentum, how do we write the forces, and how do we write the torques acting on this body. Right? Those are the things we have to deal with. Well, the linear momentum is fairly straightforward, right? It's a rigid body. It consists of a bunch of masses that are all moving at different velocities, but when you abstract this down just to a point mass, right, which is what you're doing when you calculate momentum, that's simply the mass of the body times the velocity of the center of mass, right? So the mass times the derivative of the position vector of the center of mass, right? Now, angular momentum is maybe a little bit more challenging to think about in this case. For this coordinate system, this is a body that's both rotating, right? It's spinning around, and it's also moving. And so for angular momentum, we actually need 2 components here. One component is going to be the angular momentum, where we actually think about this as angular momentum due to translation of the center of mass. So if this thing is falling like this, you can see that the angle that you're watching would be decreasing, and so that would give you some negative angular momentum about this axis, right? So that's going to be a cross product of the position vector from the center of mass with the position vector to the center of mass with the momentum of the center of mass. So that's the translational component. And then we're going to add to that translational component the angular momentum about the center of mass. So this is the moment of inertia about the center of mass times the angular velocity about the center of mass, and that is in the k-hat direction, right? And notice here that theta dot is also omega, right? It's how fast the thing is spinning. So you've got angular momentum both due to translation and due to spin. Forces in this case are pretty straightforward. There's one force and it's acting at the center of mass. So it's going to be minus mg times j hat, right? And torques are fairly straightforward as well. There's one force acting. It's at a distance RCOM from the origin, or the vector from the origin to the point where the force is being applied is RCOM. So my torque is going to be the position vector of the center of mass crossed with minus mg j hat. Okay. Now this isn't the most elegant way to go about this problem, but it works. So let's follow it through. Our equations of motion now are going to be that linear momentum has to be conserved. So if I sum the forces, that tells me what the total flow of momentum into or out of the system is. Right? So that's going to be one equation of motion. Let's follow that through. The forces, the only force is minus mg j hat. Right? My linear momentum is m times RCOM dot. So when I take the derivative of that, I'm simply going to get ma, right? M times RCOM double dot. And I could write that out in more detail as m times x double dot I hat plus y double dot j hat. Okay. So that's my first equation. Notice that I've actually got 2 second derivatives in here. I ultimately want want to have 3 second-order differential equations, but if you actually look at this, it actually is 2 second-order differential equations. Because I have an I hat component, right? X double dot is equal to 0, and a J hat component, Y double dot, is equal to minus mg times m. I guess I should be using big M here. Right? Okay. Let's now get our third equation, right? Sum of torques is the time rate of change of the angular momentum. Well, my torque here is the position vector of the center of mass crossed with minus mg j hat. Okay. And my angular momentum is a little bit more involved, right? So it's d by dt of RCOM cross PCOM, right? So the position vector of the center of mass crossed with the momentum of the center of mass. And then I've also got plus the moment of inertia about the center of mass times theta dot in the k hat direction. Okay. If I go ahead and take this derivative now, some sort of interesting things happen. When I take the derivative of the cross product, of course, the derivative distributes, and so I get r dot COM cross P, right, plus RCOM cross P dot. Right, that's what the derivative of the first term will give me. And the third term, the last term here, will simply give me ICOM times theta double dot, because the center of mass moment of inertia is not changing. All right. And finally, I can make a sort of interesting observation here, which is that this first term in the cross product is actually 0. Why is that? Well, if you look at it, the momentum is simply the mass times the velocity of the center of mass, right? And when you take the cross product of a vector, the velocity of the center of mass with itself, you get 0, right? That is, the velocity is parallel to the momentum, so this term is 0. So really we only have 2 terms here. One term is this one, and one term is this one. Furthermore, if we look back to this equation, right, we actually know what P dot is, right? P dot is simply minus mg j hat. So this is r cross minus mg j hat, right? Because we know from the previous equation what the time derivative of momentum is. And if I actually look at this now, I can see on the left-hand side I have position of the vector of the center of mass crossed with minus mg j hat. On the right-hand side I have position vector of the center of mass crossed with mg j hat. This term and this term cancel, which gives me I times theta center of mass times theta double dot is equal to 0. Okay? So via some fairly convoluted arguments here, I've gotten to some pretty darn simple differential equations. One of them is that the angular velocity is not changing. There is no angular acceleration, right? A second is that the acceleration in the x direction is 0, right? That comes from the I hat component of this equation, right? You can see there's no I hat on the left-hand side. There is I hat on the right-hand side. And similarly, the y acceleration is minus g. That's from the j hat component. Y double dot is equal to minus g. Okay? Pretty convoluted way to get there, but we got there. Let me show you the sort of simpler way to get there. The simpler way to get there is to be a little bit more intelligent about our choice of origins for different things. So we still have this situation where this is RCOM, and we're going to use that for this coordinate system for doing our translational parts of things. So for this coordinate system, the linear momentum is m times RCOM dot, right? And the forces are minus mg j hat, right? But then we're going to think about a second coordinate system just for dealing with the torques, where we actually instantaneously put that coordinate system on the center of mass, right? Still makes sense to talk about what theta is, but if we instantaneously put the coordinate system at the center of mass, there's no translational component to the angular momentum because r is 0. And so for this coordinate system, the angular momentum is simply I center of mass times theta dot, right? And the torque is 0. And so because the only force that's acting is acting at the origin for this coordinate system. So this coordinate system much more quickly gives us, sum of torques is I times theta double dot, I center mass times theta double dot, or theta double dot is equal to 0, right? And by the same token, this coordinate system pretty quickly gives us that x double dot is 0 and y double dot is minus g. So the sort of moral of this story is that by choosing your coordinate systems appropriately at different times, you can actually make your life much easier. You still get to the same answer, but choosing your coordinate system about as instantaneously located at the center of mass for doing some of your angular calculations is often quite handy.